After we have learned the general physiology and the discussion on channels, transport processes, now we will see the physiology of nerve and muscle. It will be discussed under these headings. We will discuss the resting membrane potential, action potential, and the nerve and muscle physiology. Let's begin with the first topic, that's RMP, the origin and development of the resting membrane potential. Well, the first point is that the concept of membrane potential, each cell, every cell, any cell in the body has excess negative charges lined up on the inside of the membrane, and this creates the negative potential on the membrane called as membrane potential. This is true for every cell in the body, that there are excess negative charges lined up, and this creates the negative potential on the membrane. Henceforth, whenever we discuss any potentials on the membrane, it would be on the inner aspect of the membrane. Whether the membrane is resting, whether the membrane excites, we are talking about the inside of the membrane. Well, so every cell has this negative potential. The value differs. Let's see the different values. For instance, a red cell, RBC, or an epithelial cell, for these the value is less negative on the membrane potential. It's -8 to -20 millivolts. For a smooth muscle cell, the value would be -35 to -45 millivolts. For a pacemaker cell in the heart, SA nodal cell, the value is -55 to -65 millivolts. For a nerve, the value is -70 millivolts. And for skeletal muscle and Purkinje fiber in the heart, this potential is -90 millivolts. So this is the range starting from RBC or epithelial cell, for which the membrane potential is less negative, and skeletal muscle or Purkinje fiber in the heart, it's -90 millivolts. This is the range. But basically all cells have this negative potential on their membranes. Now, there was one question, for which of the following cells the transmembrane electrical gradient is highest in the body. Which cell will have the transmembrane electrical voltage difference highest? And the options are, let's take the options, the RBC, or the skeletal muscle cell, or a rod in the retina, or hair cell in the cochlea. 4 options. And the answer is hair cell in the cochlea. Let's try to understand why. Well, when we say these are the values for membrane potential, -8 or -35 or -90, basically all these cells are surrounded by the same ECF. All these cells, they are surrounded by the same extracellular fluid having the same composition, whose potential is taken to be 0. So outside is taken to be 0 for all these cells, and inside is -8 or -35 or -90. So if I say skeletal muscle has the membrane potential of -90 millivolts on the inside, outside is taken to be 0, and therefore transmembrane voltage difference would be 90 millivolts. From these values, therefore, skeletal muscle and Purkinje fiber, the transmembrane voltage difference seems to be the highest one. But there is an exception, and the exception is hair cell in the cochlea. You see, hair cell in our labyrinth, it's a receptor cell for hearing and equilibrium. Well, hair cell is surrounded by a fluid called as endolymph, and endolymph is not the normal ECF. You know, we are considering that all these cells are surrounded by the same ECF whose value is taken to be 0 millivolts, and then inside -8 or -90 or whatever value. But hair cell is surrounded by the endolymph, which is ECF. It is an extracellular fluid, but it more resembles ICF because it has high potassium concentration. It has got a high potassium concentration, and high potassium means this endolymph has its ECF composition. It is an extracellular fluid, and over and above that composition there are excess potassium ions, and therefore endolymph, its potential is not taken to be 0, but it is taken to be plus 80 millivolts. The endolymphatic potential is not 0, but it is plus 80 millivolts. This is called as endocochlear potential or endolymphatic potential. So now it would be clear that the hair cell, its membrane potential is -70 millivolts on the inside, but it is surrounded by a fluid which is not 0 millivolts but plus 80 millivolts, which is the endolymphatic potential, and therefore the transmembrane voltage difference would be 150 millivolts across the membrane. This is the highest in the body. Therefore, transmembrane voltage difference or electrical gradient would be highest for which cell? The answer would be hair cell in our labyrinth, 150 millivolts. This makes the hair cell among the most excitable cells in the body. Because of this high potential difference across the membrane, the cations would move much faster from outside to inside of the cell, and therefore this is among the most excitable cells in the body. That was one issue about the membrane potential and transmembrane voltage gradient or electrical difference across the membranes for various cells. Now, there are two tissues for which we will use the term resting membrane potential. Well, membrane potential is a term used for every cell, but we will use the term resting membrane potential for basically two tissues, the nerve and the muscle, because these are said to be the excitable cells. These are excitable tissues. Their cells are excitable, and what is the meaning of this excitability is that their membranes excite, and the membrane potential inside of the membrane becomes positive temporarily and then again becomes negative, but that's the membrane excitation, and therefore these tissues are called as excitable tissues, and for them we use the term resting membrane potential because sometimes their membranes are resting. So resting membrane potential for a nerve is -70 millivolts. Resting membrane potential for a skeletal muscle, we are taking skeletal muscle over here, it is -90 millivolts. At other times, the membranes would excite for these cells. For all other cells, their membrane potential will remain the same forever for the life of that cell. But in this case, their membrane potential will be sometimes resting, and at other times the membranes excite, when you can call it action membrane potential. Drop the word membrane from that and you simply call it action potential when the membrane excites. What is the purpose of this membrane excitation is also very obvious. That membrane excitation is a form of signal transmission. When the membranes excite, the signals are being transmitted through a nerve to either another nerve or to the muscle. And what is the purpose of that? The purpose would be to cause muscle contraction. So muscles will electrically excite and as a result they will contract. Let us see the origin of resting membrane potential. Origin of this resting membrane potential of minus 90 millivolts. Let us consider the value for skeletal muscle. That's minus 90 millivolts. How this minus 90 has come on the skeletal muscle membrane? Now, first thing that we should understand in this regard is the equilibrium potential for an ion. Equilibrium potential for an ion. There were a few MCQs which have been asked in the recent past. For example, equilibrium potential for which ion is closest to the RMP of the muscle? The options are sodium, potassium, calcium chloride. Or equilibrium potential for which ion is closest to the RMP of the nerve? Take same four options: sodium, potassium, calcium chloride. Or equilibrium potential for which ion is highest? Sodium, potassium, calcium chloride. Well, highest equilibrium potential is for calcium. We will see that in the due course of this discussion. Alright, but first, equilibrium potential for an individual ion. Let's consider sodium. Its concentrations are 141 milliequivalents per liter on the outside and 14 milliequivalents per liter on the inside. This is the starting point for sodium. Due to this concentration gradient, sodium will start moving in. We are assuming all other ions to remain stationary. They will not move, and we are only assuming that the sodium starts moving in by its concentration gradient. As it starts moving in, two things will happen. One is its concentration gradient will narrow because the sodium is coming in. The concentration gradient will narrow, and the second thing that happens is sodium, as it comes in, it carries a lot of positive charges to the inside, and those positive charges, they will get just lined up on the inside of the membrane. So what's going to happen after a while is that an electrical gradient gets created in the opposite direction. Across the membrane, if you see, more positive charges have lined up on the inside of the membrane as compared to just outside the membrane, and therefore electrical gradient has been created across the membrane by that initial sodium movement. And at one point it so happens that the concentration gradient and electrical gradient balance out, so that there is no net movement of sodium, and you say sodium has reached equilibrium. But at that stage, at that point, what will be the charge on the membrane? First of all, that charge on the membrane would be plus, because sodium has initially come in by its concentration gradient and it has carried positive charges to the inside, which have got lined up on the inside of the membrane. So when sodium reaches equilibrium, charge on the membrane will be plus. The only question is how much will be that charge, which is called as equilibrium potential for sodium. That is calculated by an equation called as Nernst equation. Nernst equation, equilibrium potential for an individual ion is calculated by the Nernst equation. And the Nernst equation says EMF in millivolts is equal to plus or minus 61 into log of C1 upon C2. Electromotive force, the EMF, and this is the equation. So basically, to calculate equilibrium potential for an ion, we need the concentrations of that ion inside and outside the cell. Let's consider the values for sodium. 141 on the outside, 14 on the inside. That's roughly 10. Log of 10 is 1 into plus 61. The value would be plus 61 millivolts. So note down two things. One is we have taken this plus sign because sodium is a cation and initially it came in by its concentration gradient. So it caused positive charges to line up on the inside of the membrane. And therefore, when it reaches equilibrium, charge on the membrane will be plus. And the second point is when membrane potential would be plus 61 millivolts, that time sodium will be in equilibrium. There would be no net movement of sodium. Now, let's see the equilibrium potential for potassium. Potassium is 145 milliequivalents per liter on the inside and 4 milliequivalent liters per liter on the outside. So, by concentration gradient, potassium will move out initially and then it will create the electrical gradient, which will cause movement in the opposite direction. Finally, concentration gradient and electrical gradient will be equal and there would be no net movement of potassium. One needs to understand this, that concentration gradient narrows as an ion starts moving from higher to lower concentration, and at the same time electrical gradient is getting created in the opposite direction, because these two are different things. This is milliequivalents per liter, this is 1 unit, and number of charges is a different character. So it is possible that a few milliequivalent per liter moving from one to the other direction can create an electrical gradient in the opposite direction, which can become equal to the concentration gradients. So let's take the values for potassium, 145 on the inside and 4 on the outside. Putting these values into the Nernst equation, it comes out that equilibrium potential for potassium is minus 94 millivolts. There is some discrepancy in the values. It's between 94 and minus 96 millivolts. However, the equilibrium potential for potassium is minus 94 millivolts. Why minus? Because potassium is a cation and initially by its concentration gradient it has moved out. So it carried positive charges to the outside, and that means it left behind the negative charges on the inside of the cell. So when potassium reaches equilibrium, charge on the membrane will be minus. Now, next point is When sodium moves and equilibrates, the charge on the membrane will be plus 61 millivolts. When potassium moves and equilibrates, charge on the membrane is minus 94 millivolts. And now let me make the next sentence, and that is, if the sodium and potassium both moved, both reached equilibrium, and we are saying the RMP is minus 90 millivolts, who or which ion must have been the greater contributor to the development of RMP? See, it's quite obvious. If only sodium were to move and reach equilibrium, RMP would be plus 61 millivolts. If only potassium were to move and reach equilibrium, RMP would be minus 94 millivolts. If both these ions move and they reach equilibrium simultaneously, and we are saying that the RMP is minus 90, that means potassium is the greatest contributor to the development of RMP. Potassium diffusion from inside to outside is the greatest contributor to the development of RMP. And what is the reason for that? Reason is that membrane is much more permeable to potassium. Membrane is 50 to 100 times more permeable to potassium as compared to sodium. So we can say, when sodium moves and potassium moves, potassium movement will be so great that it's the potassium movement, potassium diffusion, which will matter, and sodium movement will be negligible in front of it. And therefore, as the potassium is reaching equilibrium, it drags the membrane potential towards its own equilibrium potential. Potassium, as it is reaching equilibrium, it drags the membrane potential towards its own equilibrium potential. And that's how membrane potential, RMP, is a value which is close to the equilibrium potential for potassium. It is the potassium which has contributed maximally. And why is that? That is because membrane is very highly permeable to potassium as compared to sodium. So it's the potassium diffusion which matters in the development of RMP. Now, next point, equilibrium potential for chloride minus 89 millivolts. There was this MCQ, equilibrium potential for which ion is closest to the RMP of the muscle? The answer is chloride, minus 89 and RMP minus 90. Whenever this fact is discussed, the obvious question that comes to mind is, if this value is so close, what is the meaning of this value? This value being so close to the RMP. Why can't we say that chloride must be the greater contributor to the development of RMP, because the value is so close? First of all, the value is minus. The equilibrium potential for chloride is in minus, because chloride is more on the outside and less on the inside. So initially, by concentration gradient, chloride will come in. It will bring in the negative charges which will get lined up on the inside of the membrane. Therefore, when it reaches equilibrium, the value will be minus 89. Now, what is the meaning of this minus 89 millivolts value so close to the RMP? You see, it means that it is the potassium which contributes maximally. It is the potassium which causes the RMP to be established, and the RMP being minus 90 millivolts. And equilibrium potential for chloride is so close that it means chloride hardly moves. Chloride remains in equilibrium. That's the meaning of this particular value, that potassium is the greatest contributor. It's the potassium which develops the RMP mainly, and since the RMP value is so close to the equilibrium potential for chloride. That means when the muscle is resting and its RMP will be minus 90 millivolts, chloride will also be resting, in a sense that chloride will all be in the equilibrium. So the point I am making is that when membrane potential is very close to the equilibrium potential for an ion, then the ion movement will not be that great. Ion will remain almost in equilibrium. And if the membrane potential has moved far away from the equilibrium potential for an ion, then the ion movement will be much larger. So this point needs to be clearly understood, and therefore when the membrane is resting, chloride will be in almost in equilibrium. The value is very, very close. Next point is that we have seen so far only one ion moves, and when it reaches equilibrium, what will be the charge on the membrane? We have seen that. But in the body, it does not happen like that only one ion is moving and other ions have been held constant. When we discussed equilibrium potential for an ion, we assumed that the other ions were held constant. They were not moving. But in the body, all ions will move simultaneously, and therefore our next statement should be when all the ions, all three ions, sodium, potassium, chloride, they move and reach equilibrium. How do you calculate the charge on the membrane? By the movement of all three ions together. Now, for this we use another equation. The equation is called as Goldman's constant field equation, or it's also called as GHK equation, Goldman-Hodgkin-Katz equation. Sometimes it is also called as expanded Nernst equation. It's a slight expanded version of the Nernst equation. What all things should be considered in this equation? See, when one ion was moving and reaching equilibrium, we considered only one factor, C1 upon C2, concentration gradients. Because when one ion moves, the only force on its movement would be its concentration gradient. But when three ions are moving simultaneously, then those ions or their movements are forced or they are dependent on two factors. One is concentrations of those ions or concentration gradients of those ions, and second is relative membrane permeability. Because three ions are moving and the membrane would be more permeable to some and less permeable to other, so one ion will move much more as compared to the other ion depending on membrane permeability. These two factors will decide how much these ions are moving in relation to each other. I mean, some ion is moving more, some is less. And the third factor in this equation is polarity of the electrical charge. I mean, sodium is a cation and it is coming in, chloride is an anion and it is coming in. So what will be the charge brought in or brought out by those ions? Polarity of that polarity of the electrical charge will be another factor. Okay, the equation says, the Goldman's constant field equation, it says EMF in millivolts is equal to plus or minus 61 into log of. Now instead of one ion, we have three ions which are going to move and reach equilibrium. Therefore, we will make a bigger bracket to write those three ions. And as I said, here we will consider two factors, the concentrations of those ions and the membrane permeability. for those ions. So concentration of sodium outside into permeability for sodium plus concentration of potassium inside into permeability for potassium plus concentration of chloride outside into permeability for chloride. I am taking all the higher concentrations in the numerator, higher concentrations for those ions, upon concentration of sodium inside into permeability for sodium plus concentration of potassium outside into permeability for potassium plus concentration of chloride inside into permeability for chloride. I have taken higher concentrations on the numerator and lower concentrations of those ions respectively in the denominators. So I and O are the inside and outside concentrations of those ions. We'll put the values of these concentrations and membrane permeabilities in the equation, and the value that comes out is minus 86 millivolts. So now the next thing that needs to be understood is when all three ions move, when all three ions reach equilibrium, that time the charge on the membrane will be minus 86 millivolts. And of course, potassium is the greatest contributor. That's a given fact. We've already discussed it. Potassium diffusion is the major contributor, main contributor to this developing the minus 86 millivolts. But still, we are short by 4 millivolts. You know, RMP is minus 90 millivolts for the muscle. Minus 4 millivolts is contributed directly by sodium potassium pump. Sodium potassium pump is electrogenic. We have already discussed this, that it creates slightly negative value on the inside, and therefore minus 86 minus 4, it's minus 90 millivolts. This is the development of origin and RMP, origin of and development of the RMP. Minus 86 created by diffusion of three ions, sodium, potassium and chloride, and of course potassium predominates in that, and minus 4 is contributed by sodium potassium pump. That's the development of the RMP. Values for the nerve would be different, because although ECF is same for nerve and muscle, but ICF values are different for nerve and muscle. So RMP of a nerve would be minus 70 millivolts, and in the case of a nerve, the equilibrium potential for sodium is plus 60 millivolts. You see the values are slightly different, because although ECF concentrations are same for nerve and same for muscle, but ICF concentrations would be different, and therefore C1 upon C2 would be slightly different for muscle and nerve. Equilibrium potential for potassium is minus 90 millivolts, and equilibrium potential for chloride is minus 70 millivolts. So now if I were to ask you the MCQ again, equilibrium potential for which ion is closest to the RMP of a nerve, this time the answer would not be chloride, this time the answer should be potassium, because although the principle remains the same for muscle and nerve, but since now the value is not close, it is the same value. Same value cannot be said to be the closest value. Closest means two different but close, and therefore equilibrium potential for now potassium is closest to the RMP of the nerve, not chloride. Chloride value is the same value. Well, other ions, equilibrium potential for calcium is highest for any ion. It's the calcium. It is plus 129 millivolts. almost double the value of sodium, because two reasons. One is calcium is a divalent cation. So every time it moves in, it will bring in double the number of positive charges. And secondly, C1 upon C2 for the calcium is also very, very high. Because of these two factors, the equilibrium potential for calcium is highest in the body. For other ions, equilibrium potential for hydrogen would be minus, because hydrogen is more on the inside compared to outside, so it will go out initially. It will carry the positive charges to the outside. Equilibrium potential for bicarbonate also would be minus, because bicarbonate and anion, it's more on the outside and less on the inside. So initially bicarbonate will come in and it will bring in the negative charges. So when it reaches equilibrium, the potential on the membrane would be minus. Right, that was the first topic of origin and development of the RMP and equilibrium potentials for various ions.